Yeah, good evening, everyone. Welcome to the session. So we were doing hospital analytics, which is part of our domain analytics program. Okay, and this is the day two. Today we'll be learning about the project management methodology. In our case, we'll be learning about CRISP-MLQ, cross industry standard process for machine learning with quality assurance. Okay, so this is our project management methodology which we follow generally in data analytics or data science. Okay, so let's see. So we'll be discussing about the various stages of analytics. Okay, followed by the CRISP-MLQ methodology, various steps involved in this methodology. Okay, we'll also be learning about inferential statistics, data mining concepts, data mining primer, you can say. Okay, we'll also be learning about data split. How is a structured data split in case of data mining, various error functions associated with modeling, and some special cases like overfitting and underfitting. Okay, so let's see. So there are various stages of analytics, basically 4 stages we are having. Okay, so we are having descriptive analytics, diagnostic analytics, predictive analytics, and prescriptive analytics. These basic 4 steps. Okay, the first steps involves the question why. Sorry, what? First step is what. So descriptive analytics deals with what has happened. Okay, so here we deal with the historical data. We take the historical data. Okay, and till present, we see what has happened. This is the work of a data analyst. Okay, so this data analyst, they check up to present what has happened. Okay, they prepare reports, they prepare dashboards based on this. Then there is diagnostic analytics. So this is also the work of a data analyst. So here they try to figure out why that has happened, why it has happened. Okay, here they deal with why. Previously they dealt with what. So what has happened, then why it has happened. So here this data analyst, they try to figure out if any issues have occurred during this dashboard preparation. They see a spike or a dip in the normal deviation, normal variations. Okay, so they try to figure out why this has happened. Okay, so that is diagnostic analytics. Then we are having predictive analytics. So looking at the past, looking at this dashboard or this report, okay, looking at the past data, okay, they try to figure out what will be happening in the future, what is likely to happen in future. Okay, so when we deal with future predictions, okay, or future predictions, or you can say forecast, okay, this is the work of a data scientist. Okay, this was for data analyst. Okay, and the last step is prescriptive analytics. So here the data scientists, they have to give solutions, or we can say recommendation, okay, to prevent whatever issues is likely to happen in the future, or give recommendations to further better their organization. Okay, so these are the basic 4 stages of analytics. Okay, these 4 stages also, okay, they occur in healthcare data analytics as well. Okay, we have this also in healthcare data analytics. So here the same thing, descriptive analytics, it deals with understanding the historical data, the trends, the seasonality in this data is understood in this step. Then we are having diagnostic or discovery analytics. Okay, here they try to determine what to explore next. Okay, or here why is being explored. Okay, why it has happened. Okay, so this is what, this is why. Okay, then we are having predictive analytics. Okay, here the future is forecasted. Okay, what is likely to happen. Okay, and once we find this out, what is likely to happen, okay, we can give recommendations. We can give recommendations to unearth new strategies by which we can give better solution. Okay, so this is to better the company, better the organization. Okay, now let us talk about the project management methodology here. We are having CRISP-MLQ, which is cross-industry standard process for machine learning with quality assurance. Okay, so basically, this has a total of 6 steps, 6 basic steps. Okay, previously, this was CRISP-DM. Okay, so cross-industry standard process for data mining. Previously, it was that, but now it has changed to MLQ with addition of quality assurance. Okay, which was not present in the previous methodology. Okay, previously there was no monitoring and maintenance step. This was not there, but this also had 6 steps. The first step here is a combination of the first 2 steps of CRISP-DM. So first was business understanding, second was data understanding, third was data preparation, fourth was model building. Okay, fifth was model evaluation, sixth was deployment. Okay, so previously we are having these 6 steps. Okay, now this has been changed to these 6 steps. Okay, so let us discuss a bit more about this business, various steps we follow here. So first is business and data understanding. So business understanding. Okay, so let's take an example of hospital administration, or let's take hospital staff scheduling. Okay, hospital staff scheduling. Okay, so suppose this is our use case, and we want to understand this. Okay, so hospital staff scheduling. Okay, it depends on various factors. Okay, first of all, the number of staff we are having. Okay, this is one of the features. How many number of staffs? Okay, what are their qualifications? Okay, as they are staff, so accordingly, if they are having specialty in medicine, there will be another sector. If they are having specialty in surgical operations, there will be another sector. So depending on their qualification, okay, this staff will be assigned to a certain department. Okay, also department assigned is another. Okay, so there will be n number of features on which this use case depends on. So we'll have to understand, okay, how this each of these features affect this hospital staff scheduling. Okay, so that is business understand. Okay, once we have understood the business, next step is to understand the data. Now we are having data on each of these staffs. Okay, based on this data, which person will be assigned to which department? Okay, that could be known. Okay, so depending on the data, which kind of data we are having, we'll have to assign this. Now this data again, as we know, it can be either categorical or we call it discrete or continuous data. Again, this discrete data can again be divided into two more things. Okay, nominal and ordinal. Continuous data, on the other hand, it can be divided again into two types. One is interval data and ratio data. Okay, these four together are known as levels of measurement. Okay, these four together are known as levels of measurement. So based on which level this data falls into, they will be under that category. So suppose I'm having something like bed number in the hospital. So this will, bed number is a count data basically. So it will come under categorical data. Okay, suppose we are having blood pressure level as a data. Okay, so as we know, blood pressure can be represented in decimal form. Okay, and so this can be considered as a ratio data. Okay, so like this, we'll have to figure out which data belongs to which of this levels of measurement. Okay, so there are other various things which we need to consider about the data, like if the data is structured or not, if it is big data, or if it is time series data or cross-sectional data. Okay, whether the data is balanced or unbalanced, all those things we need to consider under data understanding. Okay, so once the data and business are understood, okay, we need to go to the second step of this CRISP-MLQ, which is data preparation. Okay, so here we are having two major things to do. Okay, EDA and pre-processing. Pre-processing depends on EDA only. Okay, first we'll do EDA. EDA again is of two types. Two things we do here. Okay, here we can measure moments of business decision, moments of business decision, or we can say it is a statistical measurement. Okay, here this is the statistical measurement we do. Okay. We also have something known as graphical representation. Okay. So moments of business decision, it is of four types, four basic types. So first moment, second moment, third moment, fourth moment. Okay. And then we are having graphical representation. It is of three types, basic three types we can say. Okay, it is univariate analysis, bivariate analysis, and multivariate analysis. So anything more than two comes under multivariate analysis. Now, this moments of business decision. Okay, this we'll be discussing tomorrow in detail. But let me just give you a brief about this. So moments of business decision. Okay, we are having first moment. Okay, first moment measures centrality. Okay, it is a measure of centrality. So measure of centrality by this, okay, this will be a value which represents the whole data. Okay, so we can say this is like the average value. Okay, first moment gives us the average value. So these are measures of central tendency here. There are three main things to consider: mean, median, and mode. Okay, then we are having second moment, which is the measure of dispersion. Okay, measure of dispersion is also we are having three measures here: variance, standard deviation, and range. Third moment. So we'll be discussing this anyway tomorrow. I'll just give a brief introduction. So third moment is measure of asymmetry. Then we are having fourth moment, a measure of asymmetry is skewness. Then we are having fourth moment, which is the measure of wickedness or tailoredness. Okay. In under graphical representation, we are having univariate analysis, which is analysis of a single variable. Then we are having bivariate as well, which is analysis of two variables. So under univariate, main thing we see is histogram and box plot. Bivariate we do for we do in scatter plot. Then we are having multivariate analysis. Okay, we don't actually have a multivariate analysis per se, but we can say that pair plot or correlation plot or heat maps. Okay, these are multivariate analysis in which multiple bivariate analysis are done together. Okay, so this is all about data preparation. Okay, once data is prepared means the data from its raw form has been converted into a formatted state, okay, which can be readily used by our ML algorithms. Okay, from raw form it has been converted to a form which can be readily used by our ML algorithms. So now we can directly apply, okay, models or our ML algorithms on this. Okay, so we can apply multiple algorithms on this, okay, and find out the best model. Okay, so this multiple model can be used, then it can also be fine-tuned. Okay, it can be fine-tuned to get the better result. Okay. Once this is done, model building and fine tuning. Okay. From this, we'll now compare all the models. Okay. All the models we have used. Okay. We'll compare their performances based on a performance metric. So we'll be learning about performance metrics also. So we'll compare all the models based on the performance metric which we have chosen. Okay, based on that, which model performs the best. Okay, from this we'll choose the best model. So this is done in model evaluation step. Okay, best model we are choosing here. Once this is done, best model is chosen. Okay, next we'll be creating an app based on this best model. This app can either be a mobile app, web app, okay, any kind of app. Okay. So now you have seen we are having oximeters. Okay. It just takes your, you just place a finger inside it and it will tell you the blood oxygen level, SpO2 level. Okay. We are having this smart watches. Okay. All day they keep a track of your calories burned. Okay. They also keep track of your sleep hours. They keep track of your hydration level. Okay. So this all is possible because of this. Okay. Because someone has made an app. Okay. Which can keep track of this. Okay. App plus hardware. Okay. It results in these kind of smart appliances. Okay. Like smart watches, with your mobiles, they also keep track of this fitness and all. Okay. So it is because of this. Okay. Because an AI model has been developed. Okay. By which we can keep track of these. Okay. Once this is done. Okay. Once you have created an app. Okay. And you have deployed this app. Okay. You need to now constantly monitor this. Okay. You need to constantly monitor this. And if we find any discrepancies, means if we are not getting the prescribed accuracy, okay, we need to now update the app. Okay, so this is how our whole CRISP-MLQ methodology works. Okay, so starting from raw data to an app which can keep track of all the details. Okay, so next I'll be just showing you one of the apps that was created by Infosys. Okay, so it takes data like eligibility, claims, EMR, RIS, PIS, LIMS, other all other clinical data, financial data as well. Okay, and it takes all this data and various analytics software it uses like clinical analytics, financial analytics, operational analytics. Okay, it uses these data and it creates dashboards, meaningful dashboards like efficiency reports, financial dashboards. Okay, financial processing models, capacity reports, regulatory reports, quality and capacity modeling. Okay, and various alerts as well. If something is alarming, okay, it will create alerts also like clinical alert, quality alert. It also can do patient profiling. Okay, history of the patient and what kind of support the patient needs. Okay, this can also be found out easily. Also classical decision support. Okay, now apps like this, they can be used in a laptop, in a desktop, in a mobile phone, in a tab or tablet. Okay, so next let us learn about data mining. Okay. So under data mining, we'll be discussing two major steps. Actually, there are three steps, but we'll be discussing two major things. One is supervised learning. Okay. Another is unsupervised learning. So first, let us learn about unsupervised learning. Okay. Unsupervised learning is called so because it doesn't have any supervision. Okay. There is no supervision in this. Basically, supervision here is the training step. There is no training step involved in this. Hence the name unsupervised learning. So what happens? Let us discuss in this. We'll be having a historical data. Okay. We'll use this data. We'll use this historical data. Okay. We'll use a machine learning algorithm on this, and we'll find the hidden patterns and rules in the data. Okay. Natural patterns in the data. Okay. These natural patterns show us which data or which kind of this records are closely associated with which other records. Okay. So this close association or cluster, we can say, okay, can be found out using unsupervised learning. Now, using this rules and patterns which were discovered by this, okay, if we are getting any new data, we can cluster it accordingly. Means under which cluster or under which item or which under, we can say, which items it is closer to. Okay. So there are multiple algorithms based on which we'll have to see this. Like we are having clustering. So here we will find which cluster this new data belongs to. We are also having association rules. So here we will find this new data belongs to or is closer to which of the items. Okay. So association is basically, you can say, item to item relation. Okay. How one item is related to another item can be known using association rules. Okay. There are various others, but yeah. So as we move along, we'll be seeing all those. Okay. Next step is supervised learning. So as we discussed, unsupervised learning, there was no training phase, hence the name unsupervised learning. In supervised learning, we are having a major phase of training. Okay. And because of this, we say the data has supervision. Okay. As the data has supervision, we call it supervised learning. Okay. So let us discuss about the supervised learning, how this works. So historical data, here also we start with the historical data, but we follow it up with simple random sampling. Okay. So here the data is labeled. First of all, let me tell you that. So we know which is the output. Which column is the output column? Okay. So here we first of all divide our data set into training and test, or here we call it validation set. Okay. Training set and validation set using simple random sampling. This is done to make the data unbiased. Unbiased sampling. Okay. SRS is unbiased sampling method. Okay. Now this training data. Okay. On this, we apply machine learning models. Okay. Or machine learning algorithm to find, okay, the relation between the output and input data. This relation is represented by a mathematical equation. Okay. Once we have found this, we will test it on the validation data set. or test data set, we can also call it. Okay. On this validation data set, we will try to predict using this mathematical equation and find the outcome. Once we found the outcome, we'll compare this outcome with the original value. Okay. So this using this comparison, we can say whether this model is good or not good. Okay. And we can just fine tune this model again. If it is not showing us good results, we can fine tune this and again do the same testing. Okay, unless we are getting a good model. So once the final good model is found, we'll take that mathematical equation. That mathematical equation will be our solution. And using this on new data, okay, using this on the new data, we can predict the outcome. So this was supervised learning. So this is the data mining step. Okay, this is the data mining step. Okay, so let us discuss about this data split as well. So first of all, the data we are having, it is split into training set, validation set, and testing set. Okay, training set is we apply various machine learning algorithms on this training set, and we build a model. Once this model is built, okay, we test this model on the validation data set. If we are not getting a good result, we'll again go back to the model building, okay, and we'll do some hyperparameter tuning here. Hyperparameter tuning. Okay, so we'll do the hyperparameter tuning. Once this hyperparameter tuning is done, okay, we'll again validate. If we are still not getting good result, again we'll do some hyperparameter tuning. Unless and until we get a good result, we'll keep on doing this. If still after many tries, if you are not getting a good result, we can change the entire model itself. Okay, suppose we are trying with linear regression. Okay, but our data is not linear. It is not linearly separable, or it cannot be generalized using a linear line. Okay, so it will not give us a good result. So in that case, we can change it into a non-linear regression model. Okay, like maybe decision tree. Okay, so by doing so, we will get better results in the validation sets. Okay, now we can also do hyperparameter tuning in this case as well to get a better result. So once we have found a model that better suits our data, okay, we will be keeping aside a test data. Okay, finally, after we have gotten the model, we'll add this training data and validation data and test on this whole data. Okay, once train on this whole data. Once this is done, we'll do the testing on the test data, which is previously unseen by the data set or the model. Okay, so if here also it gives us a good result, okay, we will call this as a generalized model now. Okay, and if we got and the error here will be known as generalized error. Okay, and we also will be checking overfitting, underfitting conditions. So we'll be coming to that later. Okay, now I was talking about performance evaluation metrics. So there are few metrics which can be used to evaluate the performance. Okay, so depending on which kind of your output data is, this performance evaluation will differ. So suppose it is a continuous data. If it is a continuous data, we try to find the error. Error is nothing but actual value minus predicted value. Okay, so here we will be finding y minus y cap value. So error will be calculated. If the data is discrete, if data is discrete, we cannot, do direct subtraction and find the error. So here we'll have to do comparative analysis. Okay, so here we can find the relation between y and y cap. Okay, how close is y to the y cap, or how similar are y and y cap? So here we do comparison study in case of discrete data. Okay, so first let us discuss about this discrete data. So generally for discrete data, we'll be using confusion matrix. Okay, we'll be using confusion matrix. So what is this confusion matrix? Confusion matrix is a 2 into 2 matrix, okay, which tries to find the relation between actual value and predicted value. Okay, how close is our, or are our values to actual value, our predicted value to actual value. So from here we can find various metrics. Okay, so let us discuss them one by one. So this is the 2 into 2 matrix in which we are having actual value and predicted value. So this is actual value when it is true. This is actual value when it is false. This is predicted value true, predicted value false. So actual value and predicted value, when both are true, this point is known as true positive. Okay, when actual value is not true, but predicted value says it is true, it is known as false positive. Okay, let's write this positive, this is negative. Okay, it will be more clear. So actual value when it is true and predicted value is positive, it is true positive. Actual value when it is false and predicted value is positive, it is known as false positive. Similarly, when actual value is true, but predicted value is negative, it is known as false negative. And when both are, false or both are negative, it is known as true negative. Now, from this confusion matrix, we can find many things. Okay, so we can first of all we can calculate the accuracy. We can find the accuracy here. So accuracy is all the true values. So true positive plus true negative by all the values. Okay, so true positive, true negative, false positive, false negative, all the values. So let me write it as total. Okay, so this will be the accuracy. Now, if you want to find the error in this case, error is nothing but 1 minus accuracy. In this case, it will be false positive plus false negative by total. Okay, so these are the basic evaluation metrics which can be used. Okay, apart from this, there are many other evaluation metrics for discrete data. So let us see that those measures. So we are having precision, okay, which tells us about how many, out of all the true predicted or positive prediction, out of all the positive prediction, how many were true? How many true values we got? Okay, so it is true positive by total number of positive prediction, which is true positive plus false positive. Okay, similarly, we are having sensitivity. Okay, it tells us out of all the actual values, okay, out of all the actual values, how many were truly predicted? Out of all the actual value, how many truly predicted? So it is true prediction by true prediction plus false negative, which is true prediction, which are, we can say, actual cases, or actually uh, it was there, but false predictions were given. Okay, predictions were given as false. So basically, let me just draw it here. Okay, so if we are having true positive, true negative, false positive, false negative, if we are having this, so sensitivity, it tells us about this. Okay, actual value, this is predicted value. So it tells us about out of all the actual values, okay, how many were truly predicted? That is sensitivity. Similarly, we are also having specificity. Okay, specificity, it is the same thing like sensitivity, but here it tells us about all the negative values instead of positive. It tells us about all the negative values. Okay, so it is also known as true negative rate. Specificity is also known as true negative rate. Sensitivity, on the other hand, is also known as true positive rate. Okay. Also, there is something known as false positive rate. Okay, this false positive rate, which is just the opposite of this. Okay, false positive rate, it tells us about a type 1 error. Okay, if you are clear with hypothesis testing, we will be knowing the type 1, type 2 error. Okay. Similarly, we are also having false negative rate. Okay, which tells us about the type 2 error. We are also having a metric known as F1 ratio, which is 2 times of precision into recall by precision plus recall. Okay, and it lies in the range of 0 to 1. Okay. So these are the various evaluation metrics that can be used for a discrete data when our output is discrete, basically. Okay, next. Okay, then we are having, if our data is continuous, if our output is continuous, then what to do? Okay, so for a continuous value, as I told you, for a continuous value, we can find the error. And error is nothing but actual value minus predicted value. Okay. Now, this is the actual value. This is the predicted value. If I subtract both of this, I get error. Okay. So similarly, I'm finding error for everyone. Okay. So for this error measurement, okay, we are having many formulas, like we are having mean error, mean absolute deviation. Okay. Mean error, mean absolute deviation, mean squared error. Okay. Root mean squared error, mean percentage error, mean absolute percentage error. Okay. So we are having so many, error measures, out of which RMS and MAP are the two which are primarily used. Okay. But MAP, it gives us a percentage value. Okay. So when we are considering both of this, if you need a percentage value, a value between, 0 to 100, or, 0 to 1. Okay. We can take this MAP as a function. Okay. We can calculate using this. Now, mean error is something which cannot be used. Okay. Because you can see, if we consider mean error, it gives us, it might give us 0 value, because it is just summation of all the values. So the direction of the error is subtracts the direction of error. Okay, and it gives us a lower error value that is there. Okay, it might even lead to zero error. Okay, which is not true. Okay, so we can use either of these. Okay, mean error cannot be used because it might not give us the correct result. Okay, and here from here RMSE and MAPE is something which we consider the most. Okay, so from this we see forecast of model 1, and there is also model 2. Okay, model 2 we can see we are getting higher error. Okay, we are getting higher error. So this higher error model will not be chosen because this is giving us greater amounts of error. So in our so all our projects are basically, we can say, optimization problem. Okay, here we are trying to minimize the error. Okay, here we try to minimize the error. So a higher error will not be a good result. Now, why do we need this mean error? So if mean error value is 0, we can say that this is an unbiased model. Okay, it can only be used for this, or near to 0, you can say it is an unbiased model. Okay. Now, overfitting and underfitting. Before this, let us learn about these things, variance and bias. So what is bias? What is variance? Bias, we can say that it is a training error, error in training data. Okay, training error. Okay. Bias is training error, error. Variance, we can say it is test error. Okay, so condition where training error is 0 or very less or very close to 0, and but the test error is very high. Test error is high. Okay, suppose that, then this is a overfitting condition. Overfitting condition. Similarly, we are having another, where we are having a higher training error. Training error is high. Suppose that test error will also be high, because if training is not done properly, test will be also faltering. So if this is the case, it is underfitting condition. Okay, this is underfitting condition. Okay, so if we just see this in a chart, okay, so this is regarding a regression problem or a continuous data. This is a continuous data. Okay, this is regression, this is classification. So a regression problem. Okay, so this is the data we are having like this. So this green line is what the actual solution is. Okay, but here we are trying to solve this using a linear function, a linear equation. So we will be drawing a line with minimum errors. But this line with minimum errors, this won't be able to generalize the whole equation. So we do not require a data like this or a model like this. We'll require a polynomial model. Okay, with polynomial model, we can capture, correctly. Okay. So we can say this is a right fit model. This is underfitting. First one is underfitting. This is right fit. We can call this as overfitting. So both the cases we are having this same thing. Okay, and now we can see all the data. Our model is trying to capture data from all the data points. Okay, when this happens, this is known as a overfitting problem. Okay, here the data is trying to fit over all the data points. Okay, so there might be some errors also. So it is also trying to manage that error in our data set. Okay, so this is not a correct, you can say, modeling process. Okay, here we'll get overfitting issues. So in training, we'll get 100% accuracy, but in test, while doing testing, it will not get better accuracy. Okay, and in classification also, so we are having this circles as one class, axis as different class. So you can see using a straight line, we cannot generalize it. But using a curved line, we were able to generalize this, but with some errors. And when we did overfitting conditioning, okay. So this two data set we are trying to remove. So if our data falls here now, X is here. Suppose a new data comes up, it is here. Okay. So now we'll not be able to generalize this. Okay. Hence we'll get an error. Or not error, we will not be able to define that point. Okay. So this is or correctly define that point. So this is all about evaluation and various special cases of this model evaluation, which is underfitting and overfitting. Okay. And here we'll be choosing the training, validation, and test data set. Okay. So for that, we'll have to split the data randomly. As I discussed, simple random sampling will be used to avoid bias. Okay, training error. Now we can take either 60% of data into training, 20% into validation, 20% into testing, or we can take 80% into training and 20% into testing also. Okay, and if you are having a large test set, okay, it will be very hard to estimate future. So training set should be as large as possible. Okay. If test set is larger, will not get better estimate. So large training set will get better estimates, we can say. So these are various steps you should be following. Okay, so underfitting versus overfitting. Let me just define this here. I already told you what happened. So this is the basic definition we are having. So overfitting, it is a statistical model when it is said to be overfitted when we are training with a lot of data. Okay. And the model gets trained with so much data that it starts learning from the noises and the inaccurate data entries in the data set. Then the model will not be able to recognize or categorize the data correctly because of too many details or noise. Okay, that is an overfitting condition. Okay, so here we'll be having a very good model. Okay, or complicated model, you can say, complex model. But the data will be too simple for it. Okay, too simple data. If you are having the data too simple, will not be able to capture or will be able to capture the noise as well. Okay, but in underfitting case, the model is simple. We'll be having a simple model, and the data will be complex. Okay, so here we'll not be able to capture, the intricacies of this data. Okay, so training only will get, or we can say bias will be higher. In this case, bias will be higher. Okay, so to get a good model, we want both our bias and variance to be low. Okay, so this is all about our CRISP-MLQ methodology. Okay, so Tomorrow we'll be talking about various pre-processing methods, EDA. Okay, we might be able to see a data set related to this also. Okay, so thank you everyone for attending the session and have a good day. We'll be meeting again tomorrow again. Thank you.